Hello students. So till now we have seen what is SVM, support vector machine, in detail. Today I will cover a few more topics related to support vector machine. Specifically, what do you mean by maximum margin linear separators? So before understanding this topic, let us quickly recapitulate what is support vector machine. So as you all know, a support vector machine is a discriminative classifier formally defined by a separating hyperplane. In other words, given labeled training data, which is nothing but your supervised learning, the algorithm, that is your SVM, outputs an optimal hyperplane which categorizes new examples. So in two-dimensional space, we have this hyperplane, which is a line dividing a plane in two parts, where in each class we have got two classes lying on the either side, and there is an optimal hyperplane that separates both the classes. So we have already covered in the previous video, but still we shall quickly summarize what does it mean. So by looking at the plot, we can see that it is possible to separate the data. Yes or no? Yes. We could trace a line and then all the data points which are representing men, which is denoted by the plus sign, will be above the line, and all the women will be below the line, denoted by the red circles. Such a line that separates both these data points is called a separating hyperplane. So this black color line represents your separating hyperplane, or sometimes called as the decision boundary. If it is just a line, why we call it as a hyperplane? Good question. In this example, we have seen data points lying in a plane. So this is just a line because it is we have considered only two classes that are separating with the help of a line. But in general, SVM can work with any number of dimensions. So if we consider one dimension, then the hyperplane is called as a point. If it is two dimensions, it is called a line. So if you can see over here, this is your two-dimensional data which is represented, and the decision boundary acts as a line. If it is three dimensions, then definitely it's a plane. And if you have got more than three dimensions, then we call it as a hyperplane. I hope this point is clear. So one-dimensional data, SVM, and its hyperplane. So we can see over here the red color represents a point. When you have got two dimensions, R of n, where n represents the dimension, so it is nothing but your line. And when we have got n to be 3 dimension, it is nothing but a plane, and n dimension represents your hyperplane. Now, coming to the actual topic of today's session, maximum margin linear separator. I've already emphasized on this topic in the previous video lecture, but let us study in depth. So if you see the graph below, we can have several separating hyperplanes, isn't it? So we can see four hyperplanes over here in green, black, red, and gray. Each of them is valid as it successfully separates our data set with men on one side and women on the other side. If we select a hyperplane which is close to the data point, can you see over here we have taken green color as our hyperplane which is close to the data point, then it might not generalize well. So you can see over here the data points of women are very close. So if we consider another data set, generalization may be a problem. So we will try to select a hyperplane as far as possible from the data points from each category, that is male as well as female. We cannot restrict our hyperplane to only one data point like shown here. So this one is better because it is able to classify the men and the women category properly and resembles a perfect classification. Now, what is the objective of SVM? It is nothing but to find an optimal separating hyperplane. Why? Because it will help in correctly classifying our training data, and because it is the one that will generalize better with unseen data. So from these two separating hyperplanes, the black one is the optimal separating hyperplane which we are looking for. Now, as I told you in the previous class, that the margin is nothing but the distance on either side of the optimal separating hyperplane. So as you can see over here, the bidirectional arrow in red represents the margin. And on either sides of the separating hyperplane, we have got these points. Red for women and blue for men. So the data points which are lying on this margin, they are closest to the optimal separating hyperplane, and that is why they are called as support vectors. So given a particular hyperplane, we can compute the distance between the hyperplane and the closest data point. So this is the hyperplane and the closest data point. We can compute the distance through the margin. Once we have this value, we need to simply double it to get a actual margin. So if we are successful in calculating this particular distance, we have to simply multiply it with 2 so that we get the margin on either sides of the hyperplane. So a margin is a no man's land. This is in layman's term. That is, you cannot have any data points lying within the margin. There will never be any data point inside the margin. So here if you see, this is margin B, which is the margin space is comparatively less as compared to margin A. Always remember, the margin space should always be wider instead of narrower in SVM. So it can be seen that margin B is smaller than margin A. We can make the following assumptions. If an hyperplane is very close to a data point, the margin is going to be small. See over here. So if it is very close, the margin is going to be small. The further a hyperplane is from a data point, the larger is the margin. This means optimal hyperplane will be one with your biggest margin. Thus, the objective of SVM is to find the optimal separating hyperplane. And how will you get the optimal separating hyperplane? When we can find out the margin which is the maximum. Clear? So if you see over here, support vectors are nothing but the data points which are nearest to the hyperplane. The points of the data set, if we remove this, it would alter the position of the dividing hyperplane. And they are extremely critical elements of the data set, and that is why we call them as support vectors. Now we all know equation of a line, which is y is equal to mx plus c or ax plus b. When you are shifting ax and b towards the left hand side, we can write the equation as y minus ax minus b equal to 0. The equation of a hyperplane is defined as w transpose into x is equal to 0, where w and x are the vectors, and w transpose x will help us to calculate the dot product of two vectors, that is w and x. So when I consider two vectors w and x, the dot product of both these will help us to find the values. So W transpose X is equal to y minus Ax minus B. Now why to use the hyperplane equation? You must be wondering. It is easier to work in more than two dimensions when I'm using a hyperplane equation. And the vector W will always be normal to the hyperplane. Normal is nothing but perpendicular. Let us understand these reasons through an example. So, how you calculate the distance from a point, this is your point in blue, to the hyperplane which is in red. The hyperplane, as I told you all, it separates the two data groups. So, in this case, and W is nothing but the vector. Hyperplane is given by the value x2 is equal to minus 2x1. In order to simplify the given example, we are considering W0 to be equal to 0. And the equation of hyperplane is given x2 is equal to minus of 2x1. Which is equivalent to nothing but your W transpose X is equal to your 0. Now if you can see over here, this W which is there, okay, what is the value? It is basically nothing but on your X axis its value is 2 and on Y axis its value is 1. So this value is nothing but 2 comma 1. So we have taken the transpose which is 2 1 and X is x1 x2. So W transpose X is nothing but equal to Y minus Ax minus B. Note that the vector W is not a data point. Okay. Now we have found these values. Now we have to compute the distance in order to find out whether this is the maximum margin or there could be a possibility to have another maximum margin. What we do is we compute the distance between the points. Now we have considered point A and its value is nothing but 3, 4 because it lies at point 3 on x-axis and at point 4 on y-axis and the hyperplane. So it is normal or perpendicular to the hyperplane? Yes or no? This is the distance between A and its projection on the hyperplane. Now, we can view this point A as a vector. Can you see this? From the origin to A. And we can draw normal. So it is basically normal to your W. So if we project it onto the normal vector, what will happen? We are getting this vector P. I hope you have understood this. So we are considering point A. It is normal to this hyperplane, and when we consider this A to be a vector, we can draw a perpendicular line which is normal to this W, and when we extend this further, we denote it with a vector P. The goal is to find the distance between point A and the hyperplane, that is this value. So the same as your P absolute. This is called P absolute. So we know W is 2, 1 is normal to the hyperplane, as well as it is normal to your A3, 4. So how do we find out the absolute value of W? It is nothing but square root of summation x square plus y square. So it is 2 square plus 1 square, which is equal to square root of 5. Now we are considering another vector u, which is in the direction of your W. So what it is going to be? It is simply nothing but this 2, 1 you will divide with the absolute value of W. Clear? P is an orthogonal projection of A on W. So if you see, P is perpendicular. It is an orthogonal projection of A on W. So how P can be written as U, because U is in the direction of your W, into A into U. Now this U we have already found out, which is 2 upon root 5, 1 upon root 5. So this is written here, and we know A is nothing but 3, 4, and we are multiplying 2 upon root 5 plus 4 into 1 upon root 5. On simplification of this, you get 10 upon root 5, which you multiply with u value, which is 2 upon root 5, 1 upon root 5. So on further multiplication, you get 20 upon 5, 10 by 5, which is nothing but 4, 2. Now to find out the absolute value of this P, you have to simply perform the square root along with summation of your x square, y square, which is nothing but 2 root 5. Now this value which we have calculated is nothing but one side of the margin with respect to the hyperplane. So if you want the maximum margin size, what we have to do is simply multiplied with 2. So now that we have the distance P between A and the hyperplane, the margin is defined by twice your absolute value of P, which is nothing but, it was 2 root 5. When you multiply it with 2, it becomes 4 root 5. Now can you see over here? The optimal hyperplane is the one which maximizes the margin of the training data. So now what has happened in this case? We have found out this value of P, which was 2 root 5, and we have doubled to get the value of the margin, which is M1. Alright. So if you see M1, which is represented by these two blue lines, is not the biggest margin space. Why? Because if you see over here on the left hand side, there are still no data points or support vectors lying on this, which indicates you can extend this margin towards the left until it reaches this point G. So the biggest margin is the margin M2. See over here, initially it was over here. Now what has happened? We have extended our margin on the left hand side, and this is the biggest margin. So finding the biggest margin is same as finding the optimal hyperplane. Thank you.